explore how linear regression can be implemented in MATLAB. Our ultimate goal is to answer key questions such as, to what extent do environmental variables like temperature or humidity influence the risk of forest fires? Let's open MATLAB. First, we need to load the data, and to ensure that MATLAB can access the file, click on the Browse Folder button and select the folder containing the Algerian Forest Dataset.csv file. Then check that the file appears in the Current Folder panel. This confirms that MATLAB can locate the file before we proceed with reading it. Let us create a new script called week2.m. And then with the function readTable, we can read comma-separated values files. Just make sure that the name of the file matches exactly. The output of this function is stored in a variable named myDataset, which is an object of type table. In MATLAB, a table is a data type for storing tabular data where columns represent variables and rows correspond to observations. Let's explore our dataset to get familiar with this type of data structure and to see the data firsthand, which is always good practice. First of all, we find the number of rows and columns. We use the function size, and in this case, we have 59 rows and 4 columns. Next, we want to display the first 5 rows of the table. To extract a subset of the table, in MATLAB, we can use in bracket an indexing like 1:5, 1:5 selects the first 5 rows in the table. And here, colon indicates that we want to range from row 1 to row 5. Whereas colon in the second position means all columns. So we keep all the variables in the table. This syntax allows us to display a portion of the dataset where each row represents a different fire event and each column corresponds to a specific variable. Temperature, expressed in Celsius degrees, relative humidity, expressed as a percentage, the build-up index, which represents the total amount of combustible material present in the environment, and the fire weather index, which evaluates the overall risk of fires. In our context, temperature, humidity, and build-up index can play separately the role of the variable x, whereas the fire weather index plays the role of the variable y. Now we are ready to implement linear regression. We will create a new file named mylinearregression.m that will contain the function definition. We're going to write a function that takes as input the data points organized in 2 arrays. The first one, called x, contains the x coordinates of the points, and the second one, named y, contains the corresponding y coordinates. The function will return the coefficients m and q of the regression line. So this is the structure of the MATLAB function that we will write. The function has 2 inputs, x and y, and 2 outputs, m and q. And what we need to do now is simply fill in the dots. So this function will perform linear regression by computing the coefficients according to these formulas. And at a first glance, they can look a bit overwhelming, but let's simplify them by breaking the task into smaller steps. First, we will compute the results of these sums, and then we will combine the results. And before we start implementing, it's worth noting that some of these sums are repeated more than once. For instance, the sum of y appears twice, and the sum of x appears even 3 times. So we can take advantage of this and compute these terms only once and reuse them wherever needed. Now we are going to write a MATLAB code to compute these 4 terms. And the sums could be computed using for loops. However, we will do it in a more concise and readable way by leveraging the function sum. This function allows us to compute the sum of all the elements in an array. For example, sum of x calculates the sum of all the x coordinates. And similarly, sum of y calculates the sum of all the y's. To compute the last two terms instead, we need to introduce a new powerful concept in MATLAB, vectorized operations. Let us consider the arrays x and y containing the elements xi and yi respectively. The operation x dot star y creates a new array, whose first entry is the product of the first entries of x and y. The second entry is the product of the second entries, and so on, all the way up to the last element. Please notice the dot before the star, which indicates that the operation must be performed element by element. As a consequence, with sum of x dot star y, we compute the sum of all the products, and we call this term sum xy. Similarly, the element-wise power operation x dot power 2 is also vectorized, meaning that it applies the power operation to each element of the array individually. So that combining this operation with sum gives us the last term we need. Very good. Now the hardest part is behind us. We just need to combine all these quantities to finalize the computation. First, we compute the number of points, which is the length of x, and then the numerator of the expression of m. Then the denominator, and then we divide numerator by denominator to obtain the value of m. And finally, we calculate q using the value of m that we just determined. And this completes the computation of the regression coefficients. Great, so we have completed all the necessary steps for the implementation of linear regression. Now we are ready to use this function on our data set. So let's go back to the week 2 script and make sure that the file mylinearregression.m is available in the current directory. Now we wonder how the temperature influences the fire weather index. So to this goal, we choose the temperature as our x using this code. MyDataset.temperature extracts the corresponding column from the dataset and stores it as our x. And similarly, the content of the column fire weather index, FWI, is stored as a variable y. These two arrays are given as input to the linear regression function, and the function returns two output, which we store as two separate variables. And please note that the order of these outputs must match the order specified in the implementation of the function. Finally, we can print the results, the regression coefficients m and q. In MATLAB, the fprintf function is used to display and format output on the screen. And here, the %f indicates that the variables should be displayed as floating point numbers. And in this case, the variables that we print are m and q. Running this code, we see the results printed on the screen. Let's now visualize the data point together with the regression line. We create a new figure, and then we use the function scatter to display the data points as small blue circles in the xy plane. Next, we use the function plot to display the regression line in red. And finally, we can enhance the plot readability by adding axis labels and a title, a grid, and a legend. And please notice that the labels passed to the function legend as inputs must match the order in which the plots were created. Running this code, a new figure appears showing the plot, and we can see that the slope is positive, meaning that an increase in temperature corresponds to an overall higher fire risk. Now let's repeat the procedure using relative humidity instead of temperature. And to do that, we just replace temperature with RH in the previous lines of code. Now, in this case, we can see an opposite trend with respect to the previous case. The slope is negative, meaning that an increase in relative humidity decreases the risk of forest fires. Having in mind the initial question from the policymaker, we can conclude that temperature and humidity play opposite role in determining the occurrence of fires. And understanding this relationship is crucial for an effective risk management. More in general, linear regression helped us to extract valuable information from the data, enabling us to quantify the relationships between variables.